Physics unlock a whole new world of possibilities for your 3D projects. You can create realistic universes, user interactions, and even games. In this lesson, we will discover the essential concepts while learning how to build a simple game. Don't worry, no prior knowledge is required. To add physics to our project, we will need to add a physics engine. It's a library that will do all the calculation for us, such as gravity, forces, collisions, and so on. In the JavaScript ecosystem, there are many physics engines that you can use, such as Rapier and Canon.js. And to make our lives even simpler, Poimandress, the collective responsible of React 3 Fiber, wrapped the two libraries with useCanon for Canon.js engine and React 3 Rapier, the one that will use a wrapper around Rapier. Both are pretty similar, but I decided to go with this one, but the concepts we will learn work for both. So it's easy for you to switch from one to another. First, let's add it to our project. Yarn add at React 3 Rapier. We can restart our development server and hide the terminal. Let's open our app and create a physics world. It will contain all the physics objects of our scene. So what we will do is wrap experience wix from React 3 Rapier. So far, nothing happens, which means that if you don't decide an object is related to physics, it won't. It will just display it as normal. To add physics to an object, we need to add a rigid body around it. It's a component that will make our object react to the physics world. Let's go to the player component and our mesh. We will wrap it within a rigid body. If we reload, we can see our cube is disappearing and falling. This is because now our cube responds to gravity and it falls. Nothing is stopping it. We need to tell our floor to also react to physics. Go to Experience, This is this mesh that acts as the floor. Wrap it within a rigid body and save. Now both of them are falling. We need to tell that the floor is fixed. We add type is equal to fixed. Now it looks like the starter pack, but instead we have a cube that is falling because of the pressure of gravity, but the floor is blocking it. Let's play with forces and move our cube on that plane. Let's go to App and add the keyboard controls that we have already seen in the events lesson. First, we declare our controls, so forward, back, left, right, and also jump. Then we create a map for all our keys, and we wrap everything within keyboard controls. And we define the keys, so it's our map, and we assign it. We want to handle the key pressed in the player component. Let's go here, and we will use another way to detect that a key is pressed. What we can do is use an array, and the second parameter will be a get method. We'll be using use keyboard controls. Now with the get method, we'll be able to see if a key is pressed or not easily. We'll do it in a use frame. If get, so we call get dot, then brackets, and the key we want to detect. So controls from app dot, and we have the different ones. Forward, we'll put our logic here. And we do the same for the other direction. Forward, back, left, right, and also jump. Now to be able to apply forces to our rigid body, it's not to the mesh, it's to the rigid body, which is the physics object. We create a reference to it. We'll name it RB for rigid body. We declare it is equal to useRef. There exist two methods to apply forces to an object. Either apply apply impulse to really apply one shot of a force, or set linear velocity to define the constant speed of our object. Let's start with apply impulse. We will create a vector where we will store the impulse we want to apply. Impulse is equal to new vector 3. We do it here to not create a vector 3 at each frame. Then at each frame, we reset the values of our impulse, so 0, 0, 0 for each axis. And when we press forward key, we will do impulse dot z minus is equal to, and we will declare a movement speed constant. So go here, const movement speed is equal to 0.5. We do the same for back, but it's plus. For left, it will be on the x-axis, and for right, x-axis, but positive. The jump, we will do it later. And what we can do is rb.current.apply impulse. We pass our vector 3 impulse, and true. To wake up the rigid body if it stopped at any point to react. Now, if we try, we can move, but it's a very slidey and take making too much speed. To fix that, we have many options available to make our physics world react better. First, we can adjust the friction of the ground. So on our rigid body, we increase the friction. Let's put a higher value, for example, 5. Now if we try again, our cube rotates because the friction is too powerful on the ground and it pushes forward our cube. If we want to avoid that behavior, we can go to our player, and on our rigid body, we lock the rotations. Now it shouldn't be able to rotate and slide less than before. But it's not perfect. It's still now it should wouldn't be able to rotate and slide less than before. But it's not perfect. It's still sliding a bit. We could adjust the linear damping of the cube to make it more natural, but we won't follow this path. Instead of using apply impulse, we will apply a linear velocity. Let's rename our vector to vel, so it reflects what it is. Rename it everywhere, or instead, you can press F2 and rename it in a glance. And instead of applying an impulse, we set linear velocity with setLinVel and we save. But now our cube is moving very, very slowly. So let's adjust the movement speed. Instead of 0.5, and we save. But now our cube is moving very, very slowly. So let's adjust the movement speed. Instead of 0.5, we will put 5. Let's try to move, and now it's perfect. When we stop, it doesn't slide for an hour, it just stops moving. Let's add the jump movement. So if it's a jump, val.y plus equal jump force. We need a separate variable to define the jump force. So const jump force is equal to 8. Let's try it. And it's jumping, and then it's very slowly getting and we define the body if it stopped at any point to react. Now, if we try, we can 0, 0, 0 for each able to make our physics working apply impulse very, very slowly. So let's adjust the movement speed. But now our velocity 5 would try, and now when it does an up moving at the jump move, if it's a jump, y plus equal jump force. We need a separate variable to define the jump force. So const let's try it. And it's jumping, and then it's very slowly getting back to the floor. We have two issues. Here, the gravity is not the one we saw at the very beginning when our cube was falling. But also, we can jump many times while we are already in the air. Let's fix both of them. The first problem we have is because when we apply our velocity on the y-axis, we are overriding the gravity force. So what we need to do is to get the current velocity of our rigid body. So rb.current.linvel And when we are not jumping, instead we will apply the current velocity. So it's still applying the normal gravity it should. And to avoid jumping while we are already in the air, we are already and gravity flying, and when we are not jumping, and when we are not jumping, instead we will apply the current velocity. So it's still applying the normal gravity it should. And to avoid jumping while we are already in the air, we will create a variable named in the air. We'll be using a reference for it. By default, we are not in the air. If we jump, in the air dot current is equal to true, and we don't want to be able to jump. If we are able equal to chatter dot current in the air, we jump in the air dot current is equal to true, and we don't want to be able to jump. If we are already in the air, let's try it. We can jump. The gravity is too slow, but still it's nice and we will fix it later. And now we can't jump again. We will fix it just after discovering colliders. Colliders are responsible for detecting collisions between aerophysics objects. To be able physics if it's a jump, but by default Rapier automatically add collide reference for it. By default we are not in the air. If we jump in the air, dot current is equal to true, and we don't want to be able to jump. If we are already in the air, let's try it. We can jump. The gravity is too slow, but still it's nice and we will fix it later. And the air. Let's try it. We can jump. The gravity is too slow, but still it's nice. And we will fix it later. And now we can't jump again. We will fix it just after discovering colliders. Colliders are responsible for detecting collisions between our physics objects. To be able to visually see them, we can add debug to physics. Now we can't really see them. It's the line here on the border. Maybe on the plane it's a bit better, but by default Rapier automatically add colliders. Here, because we are using cubes and boxes, the collider fits perfectly the shape, so it's difficult to visualize. Instead of using the default one, on our player, we will change the type of collider. So on our rigid body, we can change colliders, and we have different options. Let's use ball. Now we can visualize the collider applied on that cube. If we move, we can see that it is our sphere that is impacted by the collision. When we do this, it's semi-automatic because it's creating the colliders for us, even if we define its type. But it will adjust automatically with the size of our mesh. If you don't want it to be automatic, either you can set it globally on the physics, but we want to do it on our rigid body. We will set colliders is equal to false, so it won't auto-generate one. And inside our rigid body, we will create a collider. Let's use ball collider from Rapier with the arcs. You can see it's a ball arcs, so you can go to the definition and see that it is the radius. So for the radius, we'll be using 1.5. And okay, let's disable temporarily lock rotations. And now if we try it, you can see that our cube movement is completely changed because the collider is different and the shape reacting to physics is completely different than a cube. Okay, so let's get back to the normal. We remove ball collider, we remove collider equal to false. Just first, let's discover the different types we have. So we have ball, it's the one we just created. Cuboid, it's the one that is created automatically. Hull, it's like wrapping a gift with a paper. So based on the shape inside, it won't be very precise, but very about wrapping it on the outside. And tree mesh, that will fit perfectly the shape. But the more complex it is, the more resources it will require. So be careful about the performances. So let's remove it and re-enable lock rotations. Our colliders are responsible to stop our objects with the physics, but we can also detect events from it. So let's add on collision, enter. What we get from it are various information about the event. We can get other from it. And inside our callback function, we will check if other dot rigid body object dot name. So we get access to the other rigid body object. So our player with what it collided, we get its name is equal, we will name it ground. If it's the case, it means we are no more in the air. So we can define in the air that current is equal to false. Currently, we didn't define the name of the other rigid body. So let's go to experience and rename it to ground. We can also get rid of the friction because we are not using it. Let's try again. If we jump, we can jump again, and we can jump again in the air only when we land. Because when we jump, the cube is falling too slowly. Let's talk about gravity. With a physics engine, you can define the gravity globally. So go on physics and change the gravity. It's an array of coordinates, so x, y, and z. Let's change it to -50. Now if we try to jump, it falls immediately. But by default, it's close to the Earth, so we shouldn't have to change it. But first, let's try to put the gravity in the other way. Let's put 5. Now the gravity is pushing our cube in the air automatically. Or instead, if we put -50 again and a bit on the side, maybe -30, you could create wind effect that will be applied to some objects based on their mass. So big objects won't react too much, but lighter ones will be pushed a lot. But as I said, the default gravity is correct. Let's keep it. Instead, we will just change the behavior of our player. To do it, we can change the gravity scale and multiply it a lot, so 2.5. If we try to move and jump, if we try to move, so 2.5. If we try to move and jump, the falling effect is quite convincing. Let's add a ball to our experience to see how they react to each other. So here we can add it anywhere. We'll be using a GLTF to load the model, and there is a model inside which is a ball. We'll need a rigid body to make it belong to the physics world. But by default, if we look at the colliders generated, because it's a complex mesh, even if it looks like a ball, it created different cuboid collider, and we don't want it. So let's create them manually. We set the colliders to false. Instead, we create a ball collider with a radius of 1, and we can move it. So like any 3D object, we can assign the position. Let's say x is equal to 3, position y is equal to 3, so it will start in the air. If we try it, we can see the ball is falling, but it's not very natural. Instead, we can play with various parameters to change it. It looks like a beach ball, and the beach ball is very light. So let's change the gravity scale to 0.2. You could also play with the mass. To make it rebound instead of falling directly, we can add some restitution. We'll set 1.2, and let's try it. Now the ball is falling nicely, and it's doing some rebound. I think it's time to prepare our game. I prepared a map in the starter pack project. I used the minigame variety pack from Kailusberg. It's an incredible royalty-free asset pack. I recommend you to give it a try. In our experience, instead of having the floor, so our ground here, we will replace it Physics unlock a whole new world of possibilities for your 3D projects. You can create realistic universes, user interactions it will require. So be careful about the performances. So let's remove it and re-enable lock rotations. Our colliders are responsible to stop our objects with the physics, but we can also detect events from it. So let's add on collision, enter. What we get from it are variables. It falls correct. To false. Instead, we create a ball collider, 0.2. You could also play with the mass. To make it rebound instead of falling directly, we can add some restitution. We'll set 1.2 and let's try it. Now the ball is falling nicely and it's doing some rebound. I think it's time to prepare our game. I prepared a map in the starter pack project. I used the minigame variety pack from Kailusberg. It's an incredible royalty-free asset pack. I recommend you to give it a try. In our experience, instead of having the floor, so our ground here, we will replace it with the playground component. We need to import it. So playground from playground. If you are curious about what it is, it's just GLTF JSX run on the models. And just I added manually receive and cast shadow. If we have a look at it, we have our map ready to use, but we don't have a ground anymore, so everything is falling down. To fix it inside our playground, within the main group, we will add a rigid body with the type fixed, and we'll name it ground so we can still jump and have the same logic. So we go on the bottom of the file, find the closing group, and just before /rigid body. So now automatically we have colliders added to our collider /rigid body. So now automatically logic. So we go on the bottom of the file, find the closing group, and just before /rigid body. So now automatically we have colliders added to our items, but it's using mainly cuboid collider. Instead, we want it to be very precise. To make it better, we can change the type of colliders with colliders is equal to, and we will be using tree mesh. Now you can see on every shape of the object, it generated many triangles to detect the collisions perfectly. So each shape, if I go here, it's more precise and it's fitting the shape of our zone. Currently, it's a bit complicated to play because the camera isn't following the character. Let's create a third-person controller. So let's go back to our player, and to have the camera following our player, we will simply add it to the rigid body. So perspective camera from dry. Refer to the camera lessons if you forget how to declare a camera yourself. We need to add make default. And the position, it will be the offset between our player and the camera position. So we'll want to be at 0, 5 to be on top of it, and 8 to be a bit far away from our player. If we give it a try, the position works well, but our camera is always looking at 0, 0, 0. We will need to adjust the look at of our camera. To do it, we need a reference to the camera. Let's name it camera. Let's create that reference. Is equal to useRef. We also create a vector for the camera target. We'll store it within a useRef. It will be a new vector 3 of 0, 0, 0. And in our use frame before doing anything, we set the camera.current.target.current.lerp. We use this vector to be able to lerp our camera looking at to give us a smooth effect. So camera target.current.lerp toward rb.current.translation. So this is how we get the position of our rigid body. But because Rapier system and Three.js system are not exactly the same, we need to convert the vector from Rapier to Three.js. To do it, we call the vec3 method from Rapier. So now we have a Three.js vector 3. And the lerp value will use 0.5. Now our camera.current.lookAt should be our camera target that is lerped towards our player. Let's our player. Let's try it. And it's our player. Let's try it. And it's nice. But here it's not very playable because when we want to go on the side, we want the camera to face the direction we are going to be a real third-person controller. Let's adjust our movement of our player. We will create a rotation speed. We'll be using 5. Now in our use frame, we will create an object, rot velocity. It will be equal to x0, y0, and z0. Instead, we will change the rotation velocity, so rot vel, and on the y-axis, it will be plus rotation speed and the rot vel of y minus rotation speed. Now before jumping, we will apply our rotation to our object, rb.current.set angular velocity of rot vel. And true. Now we can move and rotate our character, but it's always going forward on the z-axis. We want to adjust that. To do that, we need to convert our velocity vector with the rotation. We need to apply it to go in the correct direction. To do it, we declare a Euler rotation is equal to Euler from rapier dot set from quaternion of rb.current.rotation to get the current rotation of our rigid body. But because it's a quaternion from Rapier, we need to call the quat method to convert it into a 3JS quaternion. Then on our vector, we apply Euler with Euler rotation. Let's give it a try. Let's give it a give it Euler. Euler with let's give it a try. We can rotate and Euler is going in front of our character. Perfect. Let's create the different parts of our game. Now if we fall forever and we want to respawn to the starting point of our game instead. Inside of our experience, we will add a very big collider below the playground. Let's do it. Here, we'll add a rigid body, type will be fixed, colliders false, we want to create it manually. We want it to be a sensor, so it won't apply physics, it will just detect intersection between our rigid bodies. We'll name it space to detect it in the events and put it below the playground. So for example, -5, but you can adjust to what you like. Inside, we add a cuboid collider and we want it to be very big. So 50, 0.5 and 50. Adjust to the size of your playground. Now, because we are still in debug, you can see the limit of our space sensor. So it's always able to catch when our character will fall. On our player, on the rigid body, because we are intersecting with a sensor, it won't be on collision enter. It will be on intersection enter, but the same applies. You get access to the other and a callback function. If other.rigidBodyObject.name is equal to space, we will call a respawn function that we will create. Our respawn function, it will be very easy. Respawn is equal to rb.current.setTranslation, and we define the value we want. So 0, y at 5, so we appear a bit in the air. And z0. Let's try it. If we jump, we reappear at the respawn point. We try it here. We appear a bit high at those 0 and set translation, and we define the value we want. So zero, y at 5, so we appear a bit in the air, and z0. Try it. If we jump, we reappear at the respawn point. Perfect. To make our game funnier, let's make this swiper move. It is located in playground, and its name is swiper double. Team Red. So this is this group here. Because we want it to be in a separate rigid body, we will take the whole group, go on top of our playground component, and separate it from the rest. Now we will be able to attach its custom rigid body. The rigid body, its type will be kinematic velocity. It will move with the velocity we will attach to it. We still want the collider to be tree mesh. We need a reference to it to apply its velocity. We apply a big restitution so it will bump us when it kicks us. And we add a name to detect collision with it. So swiper. We wrap our whole group within that new rigid body. We create our reference, swiper. Is equal to useRef. Now in a use effect, so when our playground is mounted, we will apply the swiper an angular velocity, so it will turn and rotate. Set angval and adjust to your needs. So 0, y, 3. You could make it accelerate if you want. Z, 0. And true, because the velocity is a constant, we don't need to do it in a use frame. We can do it once in the use effect. Now let's try it. We can see it rotate, but if it hits us, it's very weird, the behavior. Again, this is because of the way we make our player move. We are changing its velocity. So we are overriding the way it behaves. with the gravity or the impact with other objects. We could change to apply Physics unlock when our playground is mounted, we will apply the swiper an angular velocity, so it will turn and rotate. Set angvel and adjust to your needs. So 0, you could make it accelerate if you 0. And true. Because the velocity is a constant, we don't need to do it in a use frame. We can do it once in the use effect. Now let's try it. We can see it rotate, but if it hits us, it's very weird, the behavior. Again, this is because of the way we make our player move. We are changing its velocity. So we are overriding the way it behaves with the gravity or the impact with other objects. We could change to apply impulse, but it has other drawbacks, so it's up to you to choose using one or the other. Instead, we will do that when we are punched, we won't apply any velocity and we will react to the real world. So let's create a punched variable. By default, it will be false. We will apply our linear velocity only if we are not punched. So if not punched, and we need to detect when we are punched. So if it enters in a collision with another object, here it's not a sensor, so it will be on collision enter. If other dot rigid body object dot name we are punched. So if so if not punched, and we need to detect when we are punched. So if it enters in a collision with another object, here it's not a sensor, so it will be on collision enter. If other dot rigid body object dot name is equal to swiper, then punched dot current is equal to true. But we don't want it to last forever, so we'll add a set timeout punched dot current is equal to false, maybe after 200 milliseconds. Let's Let's try it again. And now when it punches, it doesn't stop and have that weird behavior. To finish our game, we want that when we go into our game, we want that our game behavior. To finish our game behavior. To finish that doesn't stop and have that weird behavior. And now when it punches, it doesn't stop and have that weird behavior. To finish our game, we want that when we go into that gate, we teleport to the other gate here. We already know how to do it, so let's make it. We go to the playground. We search for gate large wide team blue. It's this one. It's a mesh. It's not within a group. We'll take it. We'll create its own rigid body. Instead of having the position on the mesh and the rotation on the mesh, we can assign it to the rigid body. We need it to be fixed because it won't move. The name will be gate in and it will be a sensor. We disable the colliders and add our collider. We create it this way, cuboid collider. The arcs, we can use 0.5, 2, and 1.5. And we can adjust its position. Set it to -1, 0, and 0. Oh, it's not correct. I think we shouldn't apply the rotation to the rigid body, but just to the mesh. Let's take it back to our mesh. Okay, now it's better. We know that when we will enter this zone, we want to teleport to the other gate. To do this, we go to player. It's on intersection enter because it's a sensor. If it's equal to gate in, we will call teleport. Let's create the teleport method. Const teleport is equal to, first we need to get the position where we want to be. So we'll name it gate out. It will be scene.getObject by name. And the name of our object in our 3D scene. So in playground, it's gate large white team yellow and rb.current.set translation gate out.position. We don't have access to the scene here, so we need to use 3 hook. Const scene is equal to use 3 of state, and we get the scene from the state. Let's try it. And now we are teleported to this gate. Perfect. Our game system is pretty nice, but we have a last issue with the shadows. Here they are working correctly, but if we go far away, we don't have shadows anymore. You can see here it's broken. If you remember to the shadows lesson, we need to adjust the shadow camera of our light. First, let's increase the resolution of our shadow map size because it will be way bigger. We will also adjust the position of the directional light to be way further away. So we multiplied everything by 5. And inside it, we will create a perspective camera. We'll need a ref to it. Then we attach it to the shadow camera of our directional light, and we define the near and far properties. To be able to find those correct values to see everything and have the perfect shadows, you need most of the time to use a helper to visualize it. So as we've seen in the helper lesson, let's create a reference to our shadow camera. And we create a helper, use helper, with the shadow camera ref. And the type of helper we want is 3.camera helper. When we use a 3, we need to import everything as a 3 from 3. Now we should be able to see our helper for the camera. So you can see within that zone, so this first plane here, and the second one here, this is the zone that our camera see to cast our shadows. So you can see all the playground is within those two planes here. So we know we will have shadows everywhere. If we have a look, now we have shadows everywhere. The swiper also has its shadows, and our characters anywhere on the game has shadows. And our game is finished. You now have the fundamentals to create your own physics simulations and games with React Fiber. Don't stop here and try to create a full game with this prototype. You can also explore other physics engines or libraries to find the one that fits you best. And I also have some tutorials on my YouTube channel where I create games using React Fiber. So check them out if you want to learn more about physics, games, and multiplayer. Physics unlock a whole